All right, let's get started on Chapter 10, which is going to discuss the modern atomic theory and the periodic table. So when you look at fireworks, you see a lot of different colors, and this has to do between electron transfer between the different energy levels of atoms. So what is actually the structure that's behind this electrons transfer? What are we referring to? So we're first going to talk about electromagnetic radiation, since we need to talk about the relationship between light and electrons. And then we'll talk about the Bohr atom and energy levels. And from there, we'll start talking about the atomic structure involving the electrons and then electron structure. So if you recall, when we talked about the nuclear atom, we were saying that in the center was the nucleus, and outside were electrons. But where we left it was we didn't know anything about the electron structure. We just knew that the electrons, which had a minus charge, had to be out there because my nucleus consisted of protons, which are positive, and neutrons, which have no charge. And because of that, the electrons had to be out there because atoms are inherently neutral. So we knew that my nucleus consisted of protons and neutrons. But now we need to look at the structure behind how our electrons are organized. And remember, our reactions that we're so interested in and that we've been talking about already when writing our equations have to do with electrons, not changes in protons and neutrons, because the protons determine our element, and it's a combination of protons and neutrons that really determine our mass. And it's the reactivity that's actually determined by the behavior of our electrons. So when we talk about electromagnetic radiation, okay, this radiates from stars, it can travel through space, so it can travel through a vacuum, and it ranges from radio wavelengths to X-rays to even gamma rays. Okay. So gamma rays are the most energetic. It's an M there. And the least energetic will be radio waves. Okay. So, and in there are visible light. Okay. So what are the characteristics? Well, when we define a wave, we always talk about a wavelength, and we abbreviate it with a Greek letter called lambda. Okay. And this is the distance between peak to peak of a wave. All right. And we talk about frequency. And this is abbreviated nu. This is a Greek letter. Okay. So when we talk about waves, we have wavelength, frequency, and speed. This is how fast for light or electromagnetic radiation, this is how fast a wave moves through space. And this is basically for electromagnetic radiation, 3 times 10 to the 8th meters per second. The Old English, you'll see, is about 186,000 miles per hour. Okay. So when we talk about wavelength, it's going to go from peak to peak or trough to trough. What you'll find is right here. This is how your wavelength will be traveling in that direction. Okay. So when we talk about wavelengths, these are the longest and can even be longer than 10 to the 4th. and these are the shortest. And squeezed right here is our visible. So this ranges around 400 to 750 nanometers. Okay, or you can say 400 to 750 times 10 to the minus 9 meters. Okay, you should know this is about the 750. This ranges in the 400. And we talked about Roy G. Biv. So the order is red, orange, yellow, green, blue, indigo, and violet. And then when it's shorter than the violet, we call it ultraviolet. When it's longer than red, it's infrared. Okay, so those will bracket on either side. So gamma rays and X-rays, UV, visible light, infrared, microwave, and radio waves. And it's important for you to know the order and the order of your colors. Usually we read it this way as Roy G. Biv. Okay. Turns out that the radiation has wave-like and particle-like properties. How is that possible? What happens is this: when we look at the experiments, there are those experiments that are explained only if light is a wave. Okay, but then there are other experiments where it turned out that it can only be explained if light behave like particles of energy. These are massless, they have no mass, packets of energy, and they are called photons. Okay, now when we talk about, actually, before we move on, when we talk about our radio waves to gamma rays, this is from stars and nuclear reactions. And they're very, very lethal. X-rays, you know, we do this. It's stopped actually by dense matter. Okay, and that's why you wear a lead blanket when you go get your dental X-rays. Okay, and that's why when someone has a broken bone, we use X-rays, because the X-rays can go through your soft tissue. That's why we don't see really any of your muscle tissue, but we can see your bone. Ultraviolet, this is how you get sunburns. We need ultraviolet actually to create vitamin D in our bodies, but it's still high energy, and too much exposure to ultraviolet, as you know, can, over extended amounts of time, we start seeing that's why people start getting cataracts as they get older. So gamma rays, X-rays, ultraviolet, very high energy. Visible light, actually, there's enough energy to change compounds in your eyes, and that's how you can see. Infrared, this is heat. Microwave, this is lower energy than infrared, and this is why we have microwave ovens. It turns out that with the microwave, even though it's lower energy, water absorbs microwave radiation. And when it absorbs it, it starts to tumble. And so when it starts hitting neighboring molecules, that's what increases the heat. And we use radio waves for telecommunications, so your phone, TV, any other types of telecommunications. Okay, and these are also emitted by stars as well. All of this, the whole range, is emitted by stars. Okay, so how do we explain it? So what are we trying to explain? Well, this is what we're trying to explain. When we discovered the prism, okay, yes, it turns out that it can separate out light into a rainbow. But when you start burning things in lab and you run it through prism, you don't see a rainbow. What you see is a dark background and very specific light. colored light at various wavelengths. Okay, so why is there no rainbow? And that's what we need to figure out. So we need to figure out, and then we need to explain why it has what we call this is an emission spectrum, not a rainbow. The other thing is this. Each element possesses a unique emission spectrum. So we also need to know why each element has a characteristic emission spectrum. Okay, so what Bohr did is they tried to explain it, they couldn't figure it out, but there's a couple things that Bohr did. So what he did was he said he organized our electrons into orbits, and he modeled after the planets. In other words, he put the nucleus where the sun is, and he said, what happens if the electrons are like the planets? They're in their orbit and they can't get out. And if it does get out, then it can go from one orbit to another, but it can't be anywhere in between. Okay? So it can go here, it can go there, or if I had one here, the bottom one, it can go up, but it has to go into a designated orbit. And for this to go into an orbit or go back to its home orbit, then basically that's why we see an emission spectrum. So the emission spectrum correspond to the differences in energy between orbits. All right. So basically what he's saying is Earth can move into Mars orbit or Venus's orbit or even Mercury's orbit, but it just can't wander around the solar system. Okay. So what we have here then is when we're looking at this, let's take a look at, we'll start with an electron right here. Okay, when it's at its lowest energy orbit, the electron is in the ground state. As I move farther from my nucleus, it requires energy. Anytime I have to move up, it's going to require energy. Anytime I move back down, it's going to give off energy. When it absorbs energy, so it can move up to another orbit, okay, it's called excitation. So excitation is when my electron, it absorbs energy and it moves to a higher energy orbit. Relaxation is basically if I take an electron here and it goes back to a lower energy state. This is exothermic. Relaxation is exothermic. So how does it release its energy? It releases energy to go back down to a lower energy orbit in the form of a photon. And that is how we get specific light. Okay, so this is when an electron emits a photon. It's exothermic and moves to a lower energy orbit. Okay, so we have excitation, goes to a higher energy orbit, relaxation, releases photons to go to a lower energy orbit. And when it's in the lowest energy orbit possible for that electron is called in the ground state. Okay, so this is the Bohr model. He quantized our energy. That means we have discrete fixed units. It's not a whole range. So this electron can go from here to here, from here to here, but not the other way. So when this happens, they can orbit the nucleus at different distances and each orbit. So how does he call the orbit? He uses what we call quantum numbers or principal quantum numbers. So instead of saying Earth's orbit, it's principal quantum number 3. Okay, so he uses principal quantum numbers, abbreviated N, to define or name each orbit. Okay, when it absorbs energy, it's endothermic, and it absorbs light. It can go to a higher energy level. When it emits energy, it can relax to a lower energy level. Okay, so ground state, the lowest possible energy level. Okay, the color of light depended upon that difference in the energy level. But it was great for hydrogen, but it didn't do as good of a job for helium and beyond. So we need to fix the model. And sometimes the model's just wrong and you can't do anything with it. But when we tried to take a look at his model of an atom, in particular the structure of the electrons, the one thing that was really important that was kept was, remember how he quantized the energy levels? So he quantized the energy in an atom. In other words, you only had specific energy levels, and you can't have a whole range. Okay, so what we needed to do was to find a model of the atom in which electrons were organized and still maintain that quantization. That was a very big idea. So when we talked about electrons, at this time there are all these new discoveries made in physics, and it has in math, and it has to do with quantum mechanics. Okay, and part of quantum mechanics has to do with that we are at the point where the matter that we're looking at is so small that you can treat it as a wave or a particle. It behaves like a wave or a particle. When you have really large objects and you determine the wave properties, they are thousands of times smaller than gamma rays, so they're considered negligible. But it turns out when you have something like an electron, it's so small, it doesn't have to travel at the speed of light in order for it to have wave-like properties. So like light, electrons actually display what we call wave-particle duality. Okay, so once we know that electrons also display wave-like properties, we then try to describe our atom, and in particular the electrons, as waves. So instead of like looking at particles, we're now saying, okay, so if electrons are waves, let's look at our wave mechanics, our description of waves, and see if we can use that and apply that to electrons. Okay, so once we did that, now instead of looking at an electron as a particle, now we're going to look at electrons as waves. And when we do that, instead of being able to tell you exactly where an electron is, we're now going to be looking at the probability of finding it. Okay, so now when we talk about electrons, okay, these dots are just calculating where an electron is at for a specific atom. But as a whole, what we're doing is this actually is an orbital. So that was a throwback to trying to relate it back to Bohr's model of the atom with the orbits. When we look at orbital, this is a probability density. Okay, for finding an electron in here. Okay, so it's kind of like if you're trying to find your friend and you run late and you're going to the mall, there's a probability density that friend of yours, if you know what his or her likes are, you may not find your friend in certain shops, but you may be more likely to find them in others. So there's a probability density. If you go to a shop that you're pretty certain they're not interested in, very low probability of finding the person. If you go to where you know they have their interests or they state they're going to be going to those types of stores, then you have a high probability density. So this is a probability density of how to find your friend, or in our case, how to find your electron in a hydrogen atom. Now we have several parts that we need to call it. So we're going to break it down. So with Bohr, we just had an orbit, but now we're going to give it greater structure. We're going to have what we call a shell. So instead of orbit, we now call them shells. Okay, and they're defined by a principal quantum number. And then we're going to break down the structure for each shell. Okay, the other thing is that if this is my nucleus, the closer I am to the nucleus, the lower the energy, and that's why n equals 1 is the lowest possible energy. If you look at the difference between 1 and 2 and 2 and 3, as you climb the ladder, it's not the same difference in energy. N equals 5, if you look at that, this energy difference here is smaller than this one. So each step you take, there's smaller and smaller differences in energies. So when we look at our principal energy level, our principal quantum number, these shells, the numbers practically, it can go on forever, but practically they're integers, and we see it goes from 1 to 7. Why practically? Because we don't have any atoms, don't have any elements that are beyond our principal quantum number of n equals 7. So if you look at your periodic table, notice how the rows, we have up to 7 rows. Okay. What about within each level? Okay. So our principal quantum level, or principal quantum number, n equals 1. And the only thing in there, the way it looks, is that we have a shell. Okay. So we have, let me just explain. This is the s orbital. Okay. So when we describe the organization, we'll talk about our shell. N is 1 through 7. And within the shell, we have what we call a subshell. And in the subshell, we have our orbitals. Okay? So, and you'll see us kind of intermix these two, and I'll tell you where they're the same and they're different. Okay? So here, for principal quantum number 1, this is basically row 1 of your periodic table. We only have the s orbital. Okay, so for hydrogen and helium, you'll only find your electrons in something that looks spherical. It's not really spherical. If you think about a racquetball or a tennis ball, the probability is more on the surface of that ball rather than finding it, and you won't find it basically in the nucleus. Okay. So when we look at the electrons, so this is just describing, we were just describing the orbital, kind of like where can we put the electrons. So when we put the electrons in, it turns out electrons can spin, and when my electron spins, it generates a field, and that field can go up or down. Okay, so when we talk about it that way, then it turns out when you look at an orbital, they have to have opposite spins. So if this is my orbital, I can put one electron in. Let's just put it as up. Okay. If I put a second electron in, this is one electron, it has to be of opposite spins. Okay. So this is 2 electrons. I cannot put 3 electrons because look at, if I put it up, they're the same. Can't do it. If I put it down, these are the same. Can't do it. So based on the Pauli exclusion principle, we can only have a maximum. You can have either 1, 0, 1, and a maximum of 2 electrons per orbital. Okay. Principle quantum level 2. All right. So when we look at 2, it turns out n equals 1, you can only have 1 s. N equals 2, you can have 2 s. That's that spherical one. So s looks like a little ball. Okay. And 1s is closer to the nucleus. So that's a 1s. This is my 2s. But this looks like a sphere. Okay. And it has 2p. Now with the 2p, that's my, what we call a subshell. And within it, you have 3 p orbitals. Okay. And they're in different colors. So we have one that goes on the x-axis. So this blue one is px. The one that lines on the y-axis, the purple one here, this is py. And the orange-reddish one on the z-axis is pz. So px can hold a maximum of 2 electrons. Py can hold a maximum of 2 electrons. And pz can hold a maximum of 2 electrons. Okay, so n equals 1, this is 2 electrons here, because we only have that. 2s, n equals 2, I can have 2 here. And with 2p, since I have 3p orbitals, 2, 4, 6, I can have a maximum of 6 electrons total in row 2. Okay, 3, we'll take a look at 3. So 3s looks like that, but just bigger. 3p looks like this, but just bigger. Okay, so 3s is just bigger. 3p, same thing, but bigger. Okay, and then we have D. Okay, so when we look at, so we know what S and P look like. Now we have 3 d orbitals, and we have 5 3d orbitals. Each d orbital can hold 2 electrons. So the d subshell, okay, holds a maximum of 10 electrons. Okay, now every time you increase your principal quantum level, you're going to get a new sublevel and orbital type. So principal quantum level 1, you only have 1s. But 2, you have 2s, 2p. 3, you have 3s, 3p, 3d. 4, you have 4s, 4p, 4d, 4f. What happens to 5, 6, and 7? So it turns out for 5, we have 5s, 5p, same pattern, 5d, 5f, okay? And we have something here, but you know what? It's never filled. We never see it. Okay, and why is it never filled? Because we don't have the elements. We've never found or generated those elements. These elements now, the atoms are getting really, really large. So for 5, 6, and 7, we're going to see the S. We're going to see the P's. Okay, but see, do we see the D's? We might see the D here. Okay, and the F's, 4F, 5F, we don't see 6F, 7F, or beyond. So if you look at it, we never get to enough elements to see 7F. We never get to enough elements to see 6F. Okay, so we never get enough elements to see 7D. All right, so basically this follows a pattern, and the only reason that it looks like it's not following that pattern anymore isn't because it doesn't exist. It's just that we don't have those elements in hand. Okay, so what's the maximum number of electrons in a 4D sublevel or subshell? Okay, so for 4D, we know that we have 5D orbitals, right? Because we have dxy, dyz, dxz, dx squared minus y squared, and dz squared. And each of these orbitals hold 2 electrons. So 2 maximum here. Okay, so the maximum for, let me just change it so it doesn't, looks like I'm saying 5D. So we have 5 d orbitals. Let me write that word out. Okay, so here are the d orbitals. 2, 4, 6, 8, 10. We have up to 10 electrons. That's the maximum number. Okay, I just want to make sure it wasn't confusing that we have 5, like the number 5 total, whereas 40 is the name of this is the name of the sublevel we're referring to. Okay. What is the maximum number of electrons that can occupy the n equals 3 sublevel? So let's take a look. If you look at n equals 3, okay, and that should be, we have 3s, 3p, which we have a px, py, pz. We have 3d. Okay, and up to 3 because n equals 3. So that's dxy, dyz, dxz, dx squared minus y squared, and dz squared. Okay, and each of these can hold 2 electrons. So S holds a maximum of 2, P holds 2, 4, 6, and D holds 2, 4, 6, 8, 10. So the maximum number of electrons that can go into the shell n equals 3 is 18. Okay, let's take a look at atomic structure. So for hydrogen, we'll look at that. Okay, and then we'll take a look after that at how we handle electrons when you have more than just hydrogen. Okay, And when we do that, you have to fill it with the lowest energy up and 2 electrons per orbital. Okay, so, and then we'll take a look at what happens, because as you go higher up on the ladder, remember, the energy difference between n equals 3 to n equals 4 is a lot smaller than 2 to 3. Okay, so here's an atomic structure diagram, but the more interesting one that we really want to focus on is electron configuration. Okay, now when we record this, this is our principal energy level. This is the N number. So this is, you're going to be looking at your row on the periodic table. This is the type of orbital, and then this is the total number of electrons in that sublevel. So this p orbital has 6 electrons total in it. It's maxed out. Okay, so it's not like for px, py, pz, but the total. Okay, so, and then we'll spend some time with the orbital diagram. So really, electron configuration is the biggest one. Orbital diagram is to show you how we orient your electrons. Okay. For helium, we have 2 electrons. And so remember, they have to have opposite spin. Okay. When we write the electron configuration, we know this is my principal quantum number, n equals 1, because helium's on row 1. Okay. If we look at the orbital, it's my s orbital. And how many electrons do I have in there? 2. So this is my electron configuration for helium. This is the orbital diagram for helium. Okay, so let's continue. And what we're going to talk about now is just doing the orbital diagrams and the electronic configuration for the first 18 elements. And then we're going to try to put together patterns so that you can see how that relates actually to the organization of the periodic table. So if we look at hydrogen, hydrogen has 1 electron. So it's in row 1. Has 1 electron. And since it's in row 1, we'll do just that. And that's going to be 1s. And that's exactly how we chose just 1 orbital diagram. And since we have 1 electron, we can do an up arrow. Does it have to be full-headed or half-headed arrows? No. I usually do half-head. Your textbook likes to do double-headed. Okay. When you look at helium, it has 2 electrons. Again, it's in row 1. So again, all you need to do with the orbital diagram is just draw a 1s. Okay, because we don't go past that. And when you put in your 2 electrons, 1 goes up. And remember the Pauli exclusion principle, the other has to have the opposite spin. So it's 1s, and I have 2 electrons here, and that's where the 2 comes from. So we're going to do the same thing with lithium, but lithium is in row 2, so you should do 1s, 2s, and then fill in your 3 electrons. And for beryllium, since it's in row 2, you know you have to have a 1s and a 2s. As we continue along our periodic table, boron has 5 electrons. It's in row 2, so you do 1s, 2s, 2p. Now, if you consider the previous slide where we were looking at lithium and beryllium, you could do 2s and 2p, but the 2p would stay empty and you wouldn't put it down in your electronic configuration. Carbon having 6 electrons. Here, notice that I didn't combine the 2, but I actually distributed the electrons out. Now the reason that you do this is these 2p, or let me just say p orbitals, since you have 3, px, py, and pz, these are all the same energy So they are considered, this is what we call them, they're degenerate. And because they're degenerate orbitals, what we do is before we fill up our orbitals, like we did for the 1s and the 2s, we distribute our electrons equally before we have to fill it up. Okay? Likewise for nitrogen, because these are degenerate, we put one each. Now, when we get to the next element, oxygen, we have to pair one of them. So what you're going to do is when you get a degenerate orbital, those are ones that have the same energy, and you have multiple, so we have 3 of the P's, 5 of the D's, and 7 of the F's. The way we work it is we put in 1 electron in each until it's time to pair them, because we have no other means to do so, then we pair it. Okay? So oxygen, fluorine, again, we now have to pair it. And then when we get the neon, notice all the electrons are paired in the P shell. And this is noble gas. Okay, so when all the electrons are paired, configuration, that means all the electrons are paired. Okay, so when you look at the trend, these are the ones that I want you to focus on. So notice how helium is a 1s1 and lithium is a 2s1. It's got the 1s2 but 2s1. Well, then after neon, what do we have? We have sodium. And if you look at sodium, it's going to look like neon, and then it's going to have one more. And this one more, this is going to be the 3s. So sodium, 1s2, 2s2, 2p6, and then 3s1. So if you look at the first column, group 1a, hydrogen ends in 1s1. In group 1a, when you get to lithium in row 2, it ends in 2s1. And when you get to sodium, it ends in 3s1. So it turns out group 1a, when we look at the electronic configurations, all of them start ending in S1. It doesn't mean we don't put what's in front of it. We put everything in front. But it ends with your row number and S1. So take a look at your trends now for beryllium. This is helium, 1s2, beryllium, ends in 2s2. And if we move down after sodium, what do we have? Magnesium. Write your electronic configuration and see where it ends. So now we're beginning to see a little bit more of a trend. Okay, so sodium, oh, look at this, it's ending in S1. And since it's in row 3, notice how we are beginning to fill in our 3N shell. Okay, so here, all of these are row 3. And notice they all end in 3. Okay, so the question is, what happens in row 4? So before we get to row 4 and practice on that, let's just get a couple more terms so we can talk about what happens in row 4. So valence electrons are those electrons located into the outermost orbitals. So if you look at, let's say sodium, okay, sodium was 1s2, 2s2, 2p6, 3s1. Now, how do I know this? Well, when you look at sodium, how many electrons does it have? So if we look at the number of protons, okay, it has what? 11 protons? So to be neutral, it has to have 11 electrons. And then it's in row 3. So when we do the orbital configuration, you have to go through 1, 2, and 3. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The outermost shell has the highest principal quantum number. In this case, the largest number here is 3. So when you look at anything with a 3 in front of it, there's nothing higher. I have 1 electron in there. So for sodium, I have 1 valence electron. All the other ones are in the interior, and so they're called core electrons, and they have 2, 4, 6, 8, 10. So I have 10 core electrons. Okay, so these are the interior. You can tell because my principal quantum number is lower than the largest one. Okay, so how many valence electrons does phosphorus have? So if we look at phosphorus, phosphorus has 15, okay, protons. So it has 15 electrons total. And it's in group 5A. Okay, so with 15 electrons total, it's in row 3. So we'll do 1s, 2s, 2p, 3s, 3p, and when we fill it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So when we write our electron configuration, 1s2, 2s2, 2p6, 3s2, 3p3. The highest principal quantum number is 3. And the total number of electrons then is the 2 plus 3. So I have 5 valence electrons right here. Now notice I'm in group 5A. Okay, so what element has the following electron configuration? So 1s2, 2s2, 2p6, 3s2, 3p6. So this goes through hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Oh, we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. This is argon. Now, how can we do this so that you can read it straight from your periodic table as is counting? We have a total of how many electrons? I have 1, 2, 3, 4, 10, 12, 18 electrons. So the element that has this electronic configuration has to have 18 protons. And again, that's going to be argon. Okay, so we're working backwards. This tells me I have 18 electrons. And then to be neutral, that means I have to have 18 protons. We looked that up on the periodic table, and it gives us argon. Okay, so let's go through noble gas shorthand notation. Okay, so this is what we're going to do. So if we look at silicon, silicon has 14 protons. It has 14 electrons. Well, it's in row 3. Okay, so we know we have to go through 1s, 2s, 2p, and then 3s, and then 3p. But instead of writing everything out explicitly, we can say, listen, my 1s, 2s, and 2p, these all have to be filled in order to get to row 3. Well, if I have these completely filled, then if I only look at this part with all my electrons paired, this is the same as saying it looks like neon. So what we can do with the noble gas configuration then is start with neon and then go to row 3 where silicon is. And now I can just do the remainder. So if it's 2, 4, neon has what, 10 protons, so up to here, up to neon, I've used up 10 of my electrons. So I just have 4 electrons left. 1, 2, 3, 4. Okay, so what you would write is you would write with the noble gas configuration. You start off with the nearest noble gas on the line above, on the row above your element of interest. So you write neon, then it's going to be 3s2, 3p2. Okay. How many valence electrons do you have? You have 4 valence electrons, and silicon is in group 4a. Okay. So let's try let me just write down what the electron configuration is. Neon 3s2, 3p2, and let's move on to strontium. So strontium I'll use a different color. So for strontium, strontium is in row 5, and it has 38 protons. So to be neutral, it must have 38 electrons, and this is what we're interested in. And the noble gas at the end of row 4 is krypton. So we'll start with krypton, and krypton has 36 protons, so 36 electrons. So all I have left are 2 electrons to work with. So if we look at strontium, it's in row 5, so I know I have a 5, and the first one is S. So 5s, and I have 2 left over, 1, 2, so I don't make it to the P, so it's 5s2. Okay, so you'll be working hand in hand with your periodic table as you do this, and you start seeing that it makes it very easy once you start seeing the pattern in the periodic table. Okay, so when we look at boron, boron has 5 electrons, 5 protons, and 5 electrons. It's in row 2. So we look at the periodic table and we see that the noble nearest gas at the end of row 1 is helium. So now we get to row 2. Helium takes 2 electrons, so I only have 3 left. So it's got to be 2s, 2p. I have 3 electrons to work with. 1, 2, 3. So 2s2, 2p1. Okay. Boron is from group 3a. And it has 3 valence electrons. Okay. So you write helium for your nearest noble gas, and you go to the next line where boron is, and it's 2s2, 2p1. All right. What about the positioning of our atoms and the periodic table? Okay, so when we talked about the periodic table, basically they increased it, they organized it by atomic masses. They also looked at the reactivities, and so sometimes they might switch it. In particular, iodine and tellurium was switched because iodine behaved more like a halogen, okay, like bromine and chlorine. Okay, so when they organized it, that's how they started getting the modern periodic table. All right, so if you notice, the reason I had mentioned earlier about your group number, okay, it turns out that when they're in the same group, they have the same number of valence electrons, and so they have the same reactivity. So in other words, when we mention lithium was helium 2s1, sodium, neon 3s1, and then what do you think potassium is? Potassium is going to be argon 4s1. And notice all of these are in the same column. They're all in group 1a, your alkali metals. Okay, so they all have 1 valence electron, and that's why they have the same reactivity. Okay, so we're talking about basically noble gas configuration again, and calcium, right, is in row 4, and notice it has 2 valence electrons. What group number is it in? It's in group 2a, the alkaline earth metals. What's interesting then, if I said, well, what about strontium? Didn't we do strontium? And we did strontium. We said, oh, isn't that krypton? Okay. And 5s2? Again, it's in group 2a. If I said, what about magnesium? Magnesium's in row 3. And you would say, oh, you'd read your periodic table, the line above it at the very end is neon, and then you go to row 3 where magnesium is, and you find it's 3s2 in the second column. So all of these in the second column in group 2a alkaline earth metals has 2 valence electrons. Okay. So it turns out, as we see, in group 1a, they're all S1. In group 2a, they all end in S2. Okay, so that's why this block right here is called the S block, because I'm ending in the S's. Here, if we looked at boron, it ended in 3. So this is ended in P1. So it was like for boron, we had helium 2s1, 2p1. If you look at carbon, it was helium 2S, oh, excuse me, 2S2, 2P1, 2S2, 2P2. And this is P2. Group 4A is where I have carbon. Okay, so what happens is you'll see that the first column of the P block, it ends in P1. Second column of the P block, I end in P2. Third column of the P block, I end in P3. And it goes all the way until you end in P6. And remember, what's unique is row 1, because I only have an s orbital. So I end in P6 here. So the purple area right here is called the P block, because anytime I'm in here, I'm ending in a P. Now let's talk about the D block and the F block. The D block, notice, even though I'm in row 4, the D block is 1 less. So I'm filling my D orbitals. Okay? My F block, I have to be until I am in row 6. And that's when I start filling in my F block. Okay, so notice, I'm not filling in my valence electrons. I'm filling in core electrons here. So you want to keep this handy, because now, if you look at your periodic table and you overlay this on your periodic table, you can read off the periodic table most of your electronic configurations. Okay? So let's look at argon forest 1. Okay? So first of all, you have to know you're going to be looking at row 4. So you look at row 4. Okay? It's S1, so you're going to look at the S block, first column. So you're looking at basically potassium, okay? Because potassium's in row 4. If you look at the S block, the first column, that's where potassium is, okay? All right, so let's practice reading off the periodic table here. Selenium, here's selenium right here, okay? So if we look at selenium, then you're going to read, you're going to do the nearest, right here, you're going to look at the nearest noble gas. So we're going to write argon. Okay. Thank you. So you write argon. Now let's go to row 4. Okay, because that's where selenium is. So we pass the S block, so 4s2, because that's full. Now the D block, remember, it's going to be N minus 1. So this is going to be 3, not 4, because if N is equal to 4, then this is an interior, 3 minus 1. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Haven't gotten to selenium yet. Now I'm going to my P block. So it's 4P. And I go 1, 2, 3, 4. It's in the 4th column. So 4s2, 3d10, 4p4. Okay. What about scandium? Well, let's do the same thing. Scandium is in row 4. So we start off with argon. Then the first block here is my S block. And I'm past that, so it's got to be full. So I go 4s2, 2 columns. And then I start my D block. So it's an N minus 1. So it's going to be a 3D. And I'm in the first column of my D block. So it's 3D1. Okay. Let's practice with zinc. So zinc, you see the one there. Okay, so with zinc, Okay, where's zinc? So zinc is same thing. So argon, then 4s2. Zinc's in my D block. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's in the 10th column of my D block. So it's, I forgot my 3. Hold on, 3d10. Okay, now let's try bismuth. Bismuth is way down here, right? So this is where bismuth is. So the noble gas nearest it will be xenon. So we write xenon. And now we have to go, okay, so this is row 6. 6s2. Okay, and then, see this, the lanthanide, the 57 to 71? So this part gets inserted in here. This is my F block. And so it's an N minus 2. So it starts off with 4. So 4, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? Should be 14. Okay, and then we also have basically right here, it's inserted in between, we have a D in there. So 4F, 14. And then we've got our D block, which is 5, D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It takes us to mercury. Okay, and we're not done yet because I still haven't made it to bismuth. So I go back to my 6 because I'm in the P block. So my S block, remember, is going to have an N value. My P block will have the highest principal quantum number value. D block is F minus 1. F block is N minus 2. I am back to my P block, so it's 6. P block, so P, and I'm in the 3rd column. So for bismuth, it's going to be xenon, 6s2, 4f14, because I have to pass through my F block. Then go back up to my 5d10, because now I'm in my D block. And then I finally get to my P block to get my 6p3. So now what you can do is, in knowing how to do our electronic configurations, we can now read it straight off the periodic table. What's interesting as well is this. If you look at selenium, selenium is in group 6A. How many valence electrons does it have? 6. So it turns out for your main group elements, your group number tells you the number of valence electrons. Okay? Here with scandium and zinc, we're filling our D block. Those are your transition metals, not your main group metals. On bismuth, going back to your main group, where is bismuth? It's in group 5A. And look, it has 5 valence electrons. Okay, so now we don't necessarily need to read and write the whole electronic configuration in order to answer questions like, how many valence electrons does this main group element have? And by using the periodic table and the noble gas configuration, you can quickly and easily write the electronic configuration. You don't need to physically draw the orbital diagrams every single time. Okay, so let's practice. So if we start off at neon, this finishes row 2. Now we go to row 3, and 3s2 takes us, 3s1 is sodium, then magnesium, and then we have this gap, and then we have boron, carbon. Oh, sorry. I misread that. Not boron. That's row 2. Okay. We go back. Magnesium. There we go. Aluminum. Always sips. Silicon. Phosphorus. sulfur, chlorine, argon. Okay, so this is my S block, so 3s2, 1, 2, 3p1 is there, so it's aluminum. Okay, and all you're going to do is read this. Start off at neon, go down to the next line, and do your main group columns, because these are your valence electrons. You're going to be in the column, you're going to be in group 3A. So if you intersect group 3A with row 3, you'll see that's aluminum. Okay. Now, because of their similar number of valence electrons in your main group elements, you're going to have similar chemical properties. All right. So all your elements here, your halogens, they have 7 valence electrons. Okay. Your noble gases, they have 8 valence electrons. Okay. What about everything in group 4A? All of those have 4 valence electrons. Okay, so we can now look at the periodic table and know how many valence electrons there are. Okay, so it's the total number of outermost valence electrons, and that's the same as your group number. All right, we also have names for families. All right, so all the columns or your groups or families, they have similar chemical reactivities. Here with the rows, remember this is your principal quantum number. So for the main group, okay, it's going to be n is equal to row number. And that's why previously when we talked about the organization of our electrons, and I mentioned, oh, look at n. Well, n can go to any number, but practically it goes from 1 to 7. Notice your row numbers go from 1 to 7. Okay, so when you look at magnesium, magnesium is in column or group 2A, which is your alkaline earth metals. Okay, so you should know the names for the family for 1A, which are your alkaline metals. 2A, your alkaline earth. 7A, your halogens. And 8A, your noble gases. Okay, so the period number corresponds to your highest principal quantum number. Okay, when you look at it, I try very hard to make sure your periodic table has your A's and your B's separated out. Sometimes you'll see it numbered 1 through 18. But be aware, you want to separate out your main group, okay, from your transition elements. Your representative elements are your main group. Okay, so all of these here and your F block. Okay, so you have, these are your transition metals, okay, alkali metals. So the first 2 columns are part of your main group, and then 13 through 18 or anything with an A, those are your main group metals, or main group elements, excuse me, I have a bunch of non-metals in here. All right, so now you know the names of your groups for 1A, 2A, 7A, 8A. You know how to differentiate between main groups and transition. And you know how to read the electronic configuration off of that. And one last thing, remember this is their stair step. So everything to the left are your metals, everything to the right again, are your nonmetals, and those touching it are your metalloids. So we're just finding out that the modern periodic table can do more than just separate metals, nonmetals, and metalloids and give us the number of protons per element. But now we can start seeing how it can relate to the electronic configuration and help us determine the reactivities. Okay, so let's continue on.